Welcome. After learning about the binary systems, today we shall be analyzing some of the multi-component systems, though this lecture pertains to the equilibrium in multi-component systems. In this particular lecture, we shall be learning about the Raoult's law, how it is applied to the multi-component systems, then bubble point calculation, dew point calculation for multi-component systems, and multi-component flash. We learned these things already for the binary systems, and there will be some modifications when we are considering the multi-component systems. As we see that the natural gas most of the times have some multi-component mixtures, that is, we have more than two components in the natural gas. So, in such cases the vapor liquid equilibrium data, that is the VL data, are not generally available because of the so many variations in the compositions as well as in the operating conditions. So, we need to have some kind of equations or correlations for estimating the VLE data and the other computations necessary for such kind of systems. Now, generally what we do, that we assume ideal mixture, and as we know that ideal mixture is what, that when the both the liquid phase and the vapor phase are ideal. So, when many a times we make this ideal system assumption, so that we can simplify our computations and analysis, and generally we find that this kind of assumption is valid for the hydrocarbons, because in the hydrocarbons they are generally belong to some homologous series, they have similar behavior. So, we find that this assumption of the ideal system is not too bad. Now, first we shall go for the Raoult's law for the multi-component systems. Before we go for that, let us see what the kind of notations we are using here. We are taking P as the system pressure, this small Pj with a star superscript, we are taking the partial pressure of jth component. The star signifies the equilibrium. The Pj sat is the saturated vapor pressure at the system temperature for the jth component. Yj star is the vapor phase mole fraction in equilibrium with the liquid phase mole fraction xj of the component j. So, considering one single component, some arbitrary component j, we shall be writing the Raoult's law for the multi-component mixture. Here we must understand this Pj star and the Yj star are one and the same. They are two different ways of representing the vapor phase composition. So, let us start with the equilibrium relationship for the jth component considering ideal vapor and liquid system. So, that means in this case, as we learned earlier, that we have activity coefficient, the fugacity coefficient for the non-ideal mixtures. If we keep the values of these two coefficients as unity, we shall be getting this particular equation. Here we find that Y star j into P is nothing but the partial pressure of the component j in the vapor phase is equal to the product of the mole fraction in the vapor liquid phase of the jth component and the saturated vapor pressure, and this particular thing is a function of the temperature of the system. Now, if we rearrange this equation, what we find that the summation of the partial pressures is equal to the total pressure. This is coming from the Dalton's law. So, Dalton's law says that the summation of partial pressure is equal to the total pressure, and that means we are also summing up this particular term on the right hand side. And this summation is done for component 1 to component C. That means there are C number of components in the mixture. So, once we know this, now we rearrange this equation. This Yj is equal to Pj by P, and in this case the P is replaced by this particular factor and Pj by this particular thing. So, we find that this Yj is now represented in terms of the mole fraction of jth component in the liquid phase, and the saturated vapor pressure of the jth component at the system temperature. Now, what we do, just we rearrange the equation, and we slightly do this thing that we divide by this Pj set and we write for all component, and then when we do this, what we find, we have this particular new variable. This is the relative volatility, which is defined as the Pi set by Pj set. So this is true for the ideal system. So now we are representing this Yj in terms of the relative volatility. Now here we have this what we call this equilibrium vaporization ratio or volatility Kj, which is defined at Yj star by Xj equal to Pj set by P, or this can also be written as relative volatility as Ki by Kj, and this is how we are getting this in terms of the mole fractions of the component I and component J in the vapor and liquid phase respectively. Now, these K values may be obtained from various sources, and especially for the hydrocarbons there is this D-Priester chart. This D-Priester chart gives the K value directly for such kind of hydrocarbons, especially lower hydrocarbons. So, these are given in many standard books on the thermodynamics or petroleum. So, here are the D-Priester charts. This particular chart is applicable to find out the K values of hydrocarbons for low temperature, and here what we find that on the right hand side this is the temperature axis, which is given in degree centigrade, and on the left hand side we have the pressure, which is given in kilopascal, and here these various curves which you see here, these pertain to the K values of different components. Like here we have the methane, then ethylene, ethane, propylene, propane, and so on and so forth. Now, if we want to find out the K value for any one of these components, what we have to do, we have to first locate the temperature on this axis and the pressure on this axis, and let us see what we do. Suppose we take this particular temperature and this particular pressure, we simply join these 2 points and we choose for whichever component we want to know the K value. Suppose I want to know for methane, I just simply read out the value from here, that will be the K value of methane for this temperature and this particular pressure. So, this is quite straightforward and very easy to use. Only thing is these particular things cannot be taken directly for any kind of modeling or simulation or computer coding. So, then in that case we have to develop some kind of correlations from these data. Now, this D-Priester chart is also available for high temperature. In this case we see that the lowest temperature is -5 degree centigrade and highest is the 200 degree centigrade. On this one we found the lowest temperature was -70 degree centigrade and this was 20 degree centigrade. So, using these two D-Priester charts, we find that we can span a very large range of temperatures. On the other hand, the pressure ranges are remaining almost the same. It is starting from 101.3 kPa on both the sides, that is about 1 atmosphere. This one is going up to 6000 kPa, and whereas this is going up to 5000 kPa. Now, again we find that we have the various curves for the various hydrocarbons like methane, ethylene, ethane, propylene, etc. And the similar manner as we have just learned, that we locate the some temperature on this axis and some pressure on this axis, and when we join these two points, we get this kind of a line, and then we choose for whichever hydrocarbon we want to find out the K value. We simply read out the point of intersection here. Suppose we are going for this ethane, so I simply read out the value at this point. So, this will give me the K value of the particular component, and in this case it is ethane. So, this we find that is very straightforward way of using the D-Priester chart. Now, with this knowledge of how to find out the K and the alpha, that is the relative volatility, we are now ready to again go back to the bubble point calculation, dew point calculation, which we did earlier for the binary systems. Now, in this case, what we find that, suppose we say for the bubble point means that we are given the liquid phase composition, we have to find out the vapor phase composition when the first bubble of the liquid gets formed at a given temperature and pressure. So that means in this case we are given the liquid phase composition at any given pressure or temperature. So if it is given at a pressure, and then we have to find the temperature. If we are given the temperature, then we have to find out the pressure. The details of these things we have done earlier for the binary systems, and they can be extended for the multi-component systems, and only thing is that there will be a slight modification in this analysis. In this case, unlike the binary systems, what we are doing here, we are choosing a reference component, and which is represented by this small r. And then what we are doing, we are finding the relative volatility of all the components in the mixture with respect to the reference components like this, that is we are writing alpha IR equal to Ki by Kr. Obviously, in this case, if the R is also part of the mixture, so alpha RR will be equal to unity. Now here we find that Ki is equal to alpha IR into Kr. So Yi equal to Ki Xi, that is the equilibrium relationship, and then we replace this Ki in terms of Kr and alpha IR. So we take the summation as we did earlier for the bubble point calculation. So after taking summation, we obtain this particular equation, that is Kr summation of alpha IR Xi is equal to 1. Now to do this calculation of bubble point, these are the following steps. Here we are taking the example of bubble point temperature calculation, that is we are given the pressure and the liquid phase mole fractions of all the components. So let us assume some temperature, and this first assumption may be taken as the boiling point of the reference component. Now once we know that assume the temperature, what we can do now? Now we can find out the value of the saturated vapor pressure from some correlation, for example Antoine correlation. So we use some kind of correlation to find out the vapor pressure, or we can find directly the value of the Ki if we have a deep blister kind of chart, or we have some other kind of correlation, and this I will go from 1 to C, and this includes the reference component as well. After finding the Pi set or Ki, then what we do, we find the value of the Yi with the value of this Ki and Xi, or from this relationship assuming the ideal gas and liquid, so Pi set by P, okay, and this is also goes for all the components from 1 to C. Then what we do, we check that whether the summation of all the Y, that means the mole fractions in the vapor phase, is equal to 1 or not. In this case, we take the absolute value of this difference, and this we take as the summation, that is epsilon. Epsilon is an user defined convergence criterion to figure out that whether we have reached the solution or not. Now if we find that this is not true, then what you do, we have to again go back to do the iterations. So in this case what we do, again we find out the new value of the alpha IR, and that is done by Pi set by PR set, okay, or Ki by Kr at the particular temperature we assumed. Now here we are revising the value of the Kr by taking this 1 by this particular thing, and this we have already derived, that is this is nothing but the summation of the Yi. Now we again update the value of the PR sat, that is the saturated vapor pressure of the reference component, by this particular equation PR sat equal to Kr into P, and then what we do, that update the temperature. Now with once I go to the PR sat, again I take the correlation for the vapor pressure, put this value of the PR sat there, and back calculate the value of the temperature, and this temperature is the updated temperature, and we repeat steps 2 to 8 until we go for the convergence. Now we come to the dew point calculation. In this case we know that this is the temperature at a given pressure when the vapor will form the first liquid drop. So that means we are given the vapor composition Yi at a given pressure or temperature. As we did earlier, here also we select one of the components as the reference component, and we define the relative volatility of all the components with respect to the reference component. Here there is a slight modification in the equations, that Ki equal to alpha IR Kr. Now we are writing Xi, which is unknown to us, in terms of Yi and the Ki, and then we again take the summation of this Xi, which is equal to 1, and here we have substituted for Ki alpha IR Kr. So we get this particular equation for the summation of the I, and if we are reaching the solution, then it must be equal to 1. Now we see the steps which are used to calculate the dew point temperature. Okay, and here we first assume the temperature. Again, this can be taken as the boiling point of the reference component, and we find the value of the Pi set from some correlation, or Ki from some chart or correlation for all the components at this assumed temperature, and this includes the values of the reference component as well. Now we compute the value of the Xi from this relationship and for all the components, and then we add them up and find out whether it is matching with 1 or not. Okay? And if not, so what we do, we determine this alpha IR from this particular equations, and once we find this thing, then we revise the value of Kr from this particular equation. And after finding the Kr value, as earlier, we again update the value of the PR set in terms of pressure and this updated value of the Kr, and once we obtain the value of the PR set, we can back calculate the boiling point temperature of the reference component from the given correlation of the vapor pressure, and we repeat steps 2 to 8 until we reach the convergence. Next, we go to the multi-component flash. This we also learned for binary systems. Here with the flash, that the feed is coming, and then this feed is, after it's flashed, it is, that means it is partially vaporized and it goes into two phases. And if it is a liquid feed, it will be partially vaporized. It is a vapor feed, then it will be partially liquefied. So we get two phases out of this thing, feed, and the liquid phase has a say W is the flow rate of the liquid phase, with a XWI is the mole fraction of the ith component in the liquid phase, and D is the vapor phase, and YDI is the mole fraction of ith component in the vapor phase. With this, what we do now, we write the equilibrium flash we assume. Okay, that means we are assuming that this D and W are coming to equilibrium, and then we write the overall material balance like F equal to D plus W at steady state, and we write the component mass balance also at steady state in terms of these particular mole fractions. Now we use the equilibrium relationship, that is YDI equal to Ki into XWI, and we combine these equations, these two equations, to get something called the vaporization factor F, which is W by D, and this is equal to given in terms of the mole fractions of the vapor, the liquid, and the feed, and thus we get YDI in terms of the F value and Ki and ZFI in this. Now we also can get the value of XWI, because XWI is YDI by Ki. So we are modifying this particular equation, and ultimately when we take the summation of all the YDIs, this should be equal to 1. Okay? And now we find on the right hand side we have F and we have Ki and we have ZFI. This is given to us, and we have to find out the value of the F and Ki. So these things we have to solve for to know that how much is the F, that means what is the ratio of the liquid and the vapor generated after the flash, and the values of the Ki. Now before we go to the flash calculations, you have to ensure that we are having a two-phase mixture. So what we do this kind of checking, that Ki ZFI is more than this summation we take should be more than 1. Similarly, ZFI by Ki going from I to C, it should also be more than 1. If these two conditions are satisfied, then only we go for the flash calculation, because otherwise we will not be getting two phases. So, for knowing these fundamentals, you can refer to these two books. Thank you.